this evening. It's my pleasure to introduce our speaker tonight, Larry Lawver. It's close. Yeah, Larry. It's almost as bad as having a name like Everger. Larry has a bachelor's from Stanford, PhD from the University of California, San Diego, Scripps Institution of Oceanography. His professional experience, I would call positions, range from postgraduate research geophysicist at Scripps, geophysicist USGS Geothermal Studies Project, research associate at MIT, and since 1983 he's been a research scientist and then a senior research scientist at the University of Texas at Austin. His research focuses on plate tectonics and attempts to sort out puzzling sections of the Earth's surface with, as per tonight, or tomorrow actually, an emphasis on polar regions, tomorrow lunchtime. Interests are, not surprisingly, plate tectonics, marine geophysics, and the polar regions. He has been a scientist or the chief scientist on at least 32 scientific cruises over many, many years. He has a very long list of scientific publications, presentations from technical meetings, and I had to count this. And there's 25 pages worth of those in his CV, and many memberships in various scientific organizations. He has a fairly long list of students that he has supported and or advised, mostly at UT, but a few in other strange places like up in Anchorage. And he wanted me to say that he is a bipolar, obnoxious SOB. Bipolar, though, means in the original sense of the word, Arctic and Antarctic. And given one of our esteemed members of the audience here tonight, he wanted me to say, Jillian, that he is a firm believer in plumes. So without further ado, I would like to ask you to join me in welcoming Larry Lawver.
I'm not going to say a word about mantle flux. Anyway, this is definitely not Cuba. This is South Georgia Island in the far South Atlantic, and we were down there in 2014, and I thought this is a great picture, but also it turns out South Georgia is in some ways very similar tectonically to Cuba, which is interesting. The reason why I got involved in Cuba relatively recently, because as I said, I'm bipolar, is that Manuel Iturralde, who was president of the Cuban Geological Society and all sorts of other things, actually had worked with us at Austin from about 1992 until 2003, when he could no longer get a visa to get into this country. And they had a special symposium last year at the GSA meeting in Denver, and he was one of the invited speakers, so I figured, well, I should go back and get back involved with him. And out of that, he came and visited Austin for a couple of days, and then Ian Norton and I went down to the Cuban Geological Congress in this past April, and we're getting back involved in Cuba, and hopefully Manuel will be able to get a visa and come and spend some time in Austin. For those of you who haven't been to Cuba, yes, they do have all these old cars there, but the engines gave out long ago, and they're run by small Japanese diesel engines. And about 4 years ago, the Cuban government realized they had a gold mine, so they gave everybody auto paint and things to refurbish the cars. And they weren't all convertibles to start with, they actually cut off the top. So. But this was rather interesting. This was, I think, a bachelorette party, and they had like 22 of these lined up, and they all got in and then had their evening tour of Cuba. Oops. John told me I would get these mixed up. All right. The other thing that's remarkable about this point in time is that this is essentially 50 years since or 51 or 52 years since the essential rediscovery of plate tectonics, and giving a small bit of history, Marshall Kay, who was one of the premier geologists in the 1950s, taught everything in terms of geosynclines, which meant vertical tectonics. And plates didn't exist, and things didn't crash into each other, and there wasn't seafloor spreading. And they wound up with interesting things here. And obviously, some of these are in Spanish. I don't think many of you will need that, but anyway. But the thing that they also showed on this slide here was who actually drafted it and wound up with these very nice sort of cloud things down here. Ron Oxborough in 1968, he wrote a tremendous paper on the geology of the Central Eastern Alps. And this is, having grown up in California and gotten into geology just when people were still talking about eugeosynclines and miogeosynclines, I have to wonder how people that spent generations studying the Alps ever understood anything, because this dark area here is the Alp dolomite or the major dolomite, and it simply got wrapped around, and so you had these things where you had younger or older rocks, and then turned around, they're younger rocks, and they're overlying each other, and I can't imagine how anybody ever sorted all this stuff out. Bob Dietz and John Holden had this paper in 1966, and talked about miogeosynclines and eugeosynclines, and the only way I can remember how to keep these distinct is that mio sounds kind of like Miami, so it's sort of flat lying and it's nice limestone and stuff like that. And eugeosynclines are all the stuff that's outboard of these, and somehow one was to believe that all of these things were
done by the
I don't know how they ever understood anything using this stuff, but they also were able to get away with these wonderful little diagrams on their published figures. Plate tectonics, in a way, actually dates back to 1910 when Frank Taylor wrote a paper on the GSA Bulletin, and he showed Greenland essentially moving away from North America by matching up things which he thought were rocks on both sides. And actually, had a pretty good idea of the Labrador, opening the Labrador Sea and the Baffin Bay, and then offset on the Chicxulub Fault up here. And then in 1965, Teddy Bullard and Everett Smith published their remarkable thing on the fit of the continents around the Atlantic and the Symposium on Continental Drift. And I think a lot of people that wind up in geology, when they were in junior high, they looked at these pieces and they said, gee, those look like jigsaw pieces and you can push them back together. And so remember in 1965, we didn't have high-speed computers and all that sort of stuff, but they actually sat there and were able to calculate the match of these of South America and Africa. And the thing that's of interest is the red is overlaps and the blue are areas where you had gaps. And a lot of these overlaps here, particularly in the Niger Delta here, that's all post-breakup depositional sediments, and so it was kind of hard to actually figure out exactly where the continent ended and where the oceanic crust began, and then some of the other things are post-breakup volcanic constructions on the margin of Brazil and stuff. So when did continental drift become plate tectonics is an interesting question, and I attribute it to the hunt for Red October. Now, you may find that kind of curious, but in the book, as opposed to the movie, they have this wonderful chapter about how they were navigating these submarines without pinging down the mid-Atlantic ridge, and they were using magnetics and gravity. And that, in fact, explains why the Office of Naval Research spent a lot of money going out collecting magnetic maps in the late 50s and the early 60s, because they knew they needed it for this submarine work, and it turned out it's what actually led to plate tectonics. I think most of you probably are aware that the Earth's magnetic field reverses on a relatively random basis, and Vic Vake, who was my thesis advisor at Scripps, this is from 1961, mapped towing a magnetometer was kind of boring because they went back and forth and back and forth collecting magnetic anomaly data. But in this paper, they said the dashed vertical line represents the axis of north-south magnetic anomaly, which was continuous before slipping started. So they kind of understood, that the Mendocino and the Pioneer and the Murray fracture zones were actually transform faults that offset these magnetic anomalies. And here is the figures that they published. And you can see here there's some really nice wiggles, and clearly one can get lineated magnetic anomalies in this area here. And what Vic and his co-authors figured out is that this set of magnetics actually was remarkably similar to this set over here, and then this set here was remarkably similar to over there. And they found that there was 1,150 kilometers of offset along the Mendocino Fracture Zone and 265 kilometers offset, left lateral offset along the Pioneer Fracture Zone. And this is all about 5 years before plate tectonics really exploded. And what's interesting is Vic might have actually understood plate tectonics and discovered the whole thing, except for it turns out that the Juan de Fuca plate and the Gorda plate over here is getting so deformed because it's getting subducted over here that with these very nice lineated north-south anomalies here actually got skewed over there, and so he actually didn't recognize the spreading center at that point. At about the same time in '64, Alan Cox and Richard Doyle and Brent Dalrymple were starting to date lava flows that were coming out of these volcanoes, and they were able to figure out that, well, some of them were magnetically oriented with positive polarity, and others had negative polarity. And so they started putting together a time scale with magnetic reversals in here. And so they had the Olduvai event here, but they didn't have the Jaramillo event, which should be somewhere in here. And then Jim Hertzler and Xavier Fichon and others in '66 actually were able to map, these magnetic anomalies south of Iceland, which I guess you people are going to be going, hopefully, to see that. And this is what in the book, they knew that if they ran down the highest positive magnetic anomaly, then they were in the mid-Atlantic ridge, and so they could run in a fairly full speed without having to ping to figure out what the depth was. And so it's a byproduct of something that I think most people didn't really understand, but wound up giving the evidence that we need for plate tectonics. And this is a wonderful quote from concerning Fred Vine, and it really tells about how they finally nailed it, or how he nailed it. And the critical thing at that meeting, which was a GSA meeting, was that I met Brent Dalrymple for the first time. He told me in private discussion between sessions, we think that we've sharpened up the polarity reversal scale a bit, but in particular we've defined a new event, the Jaramillo. And I realized, and this is Fred Vine, realized immediately that with that new time scale, the Juan de Fuca Ridge could be interpreted in terms of a constant spreading rate. And that was fantastic because we realized that the record was more clearly written than we had anticipated. Now we had evidence of constant spreading. That was very important. I realized at once, having pored over the problem for so long and so recently, that with this revised timescale, it would be possible to interpret the Juan de Fuca anomaly sequence with essentially a constant rate of spreading. To me, at that instant, it was all over bar the shouting. So that's essentially how they came about. And in his paper, and this is remarkable, this was a paper in Science, it was 10 pages long. Nowadays, to get a 3-page paper in Science is remarkable, and I don't think anybody's had a 10-page paper in Science in many decades. But you can see here, this is the Mendocino and the Pioneer and the Murray fracture zones, and these are some of the magnetic anomalies that Vic Gauthier was seeing. And then also, this is also in Fred Vine's paper, where he showed the magnetic anomalies across the Juan de Fuca Ridge. And what he did, he simply, this is a bit of a tease, but he simply reversed that set, and reversed this set, and this set, but was able to match them up to a constant spreading rate for both the East Pacific Rise and the Juan de Fuca Ridge, with, of course, very different spreading rates. And then at about roughly the same time, same year, Neil Opdyke and others were looking at deep, long cores that were taken in the South Atlantic, in the Southern Oceans, and they were able to do magnetostratigraphy on them, and they were actually able to come up with, for these two cores here, which were down here, and I think this one was over here, and they were able to match up a really nice spreading constant deposition rate with the magnetic reversals. So they were able to use both the earlier ones were using the declination, and this was using the inclination on the magnetic anomalies. And then this is where I was incredibly fortunate, because when I was taking geology at Stanford, and Bill Dickinson was still teaching vertical tectonics, and I said to the TA, I said, this just doesn't make any sense. And he basically said, well, if you promise not to tell anybody, this is what's really going on. And that's how I got hooked, because they had just had this major conference at Stanford where they were looking at the offset of the San Andreas Fault, and it was absolutely, there's no other way to explain the geology on the west side of the fault versus the east side without assuming a 400-kilometer offset on the fault. And that meant that, you know, it's really hard to explain a 400-kilometer offset with just vertical tectonics. And it's also interesting that Alfred Wegener back in 1929 actually showed the San Andreas Fault coming through here as a left lateral, right lateral, offset fault. And these, if you looked at the thing, you know, there were all sorts of different reasons why these two areas had to match up, and you were going from like deep water into totally shallow water, and vice versa. And then Dan McKenzie and Bob Parker in '67, which was exactly 50 years ago, sort of answered how you could, because at the same time there were a lot of people who were talking about expanding Earth and stuff like that, trying to explain all this stuff and things. And Dan McKenzie and Bob Parker were able to show geometrically how you could have subduction along Japan and Korea and stuff like that, and then have the San Andreas Fault here, and have a Mendocino Fracture Zone with a subduction zone and stuff. And so it was really an exciting time to be studying geology and geophysics. And this one, Roger Larson and Bill Menard and Stu Smith had a paper in Gulf, California, and you can see here that by this time, by '68, the Jaramillo event was a major thing, and that was able to see it here quite well. And actually, when I was putting all this together, Jim Hertzler, they actually had a typo here. And the Jaramillo event should have been from 0.89 million years to 0.95 or something instead of 1.95. But they did show that given the for the Indian Ocean and the Pacific and the North Pacific and the South Pacific, you could get very nice sort of relatively constant spreading rates, but then sometimes you had a major change in the spreading rate as things went along. One thing I will mention, because I have worked in the Arctic, is that the Russians, if you go back far enough, the Russians actually were firm believers in plate tectonics, and they had mapped these very nice magnetic anomalies also so that their submarines could navigate down the mid-Atlantic ridge. And they actually came up, Karasik and others came up with a very good match to presumed spreading rate. What's interesting in this paper here with Peter Vogt is there were all sorts of different time scales running around, and it took a while to start focusing in on which time scales one should use. And here, M naught, which is now defined as the base Aptian, Roger Larson and Tom Hildy had a time scale where this was dated at 108 million years ago. And now, if you look at the geological time scale for 2016 by Ogg and Gradstein, they have it M naught being at 125 million years ago, which causes all sorts of problems. And most of us, we actually put it at about 120. So there's still a fair amount of controversy going on. This is getting a bit esoteric, but they've defined what the base of the Aptian was, and that was the M naught. And it varies between 119, and I showed you 108, 121, 125, 114, and now it's 126.3 according to the geological time scale of 2012 and 2016, but it's only 120.95 based on what we would like to use is this 2012 and GM Kent. So there's still a lot of differences going on this. But the reason why time scales are important is if you wind up using the geological time scale of 2016, it puts this major, the Antam Java plateau, which was a major outpouring of basalt, it puts it after the whole thing started, when in fact it should be probably before, which caused a major anoxic event around the world. So, okay, moving on to plate tectonics. So this is an old slide from NASA and company, and it shows in general the major plates, and it was asked beginning how many plates there are, and if you want to just look at major plates, you could probably get by with 15 or 16, but when you look at something like Alaska, I think we have 277 in Alaska and northeastern Siberia, because you get these little bits and pieces, and one comes from Siberia at one time and another one comes from somewhere else, and you can't really say they were all the same plate, because you want to be able to go back in time and move them around. So one of the most exciting things that happened was Dave Sandwell and Walter Smith started doing satellite altimetry and taking a derivative of it and getting a gravity that then they could convert into bathymetry, and that opened up the whole world, because in the past you had just maybe a few ship tracks down here, and now you could actually see a tremendous fracture zone running all the way from where it gets through here and stuff. And then also you can see the Hawaiian hotspot track going up into the Emperor Seamounts. And so that made a huge difference on the whole thing. One of the things I will mention is that Sylvia Earle kept referring to Google Earth as Google Dirt, because they only had the continents and they didn't have anything in the oceans. And so finally they started showing the oceans, and Dave Sandwell said, well, gee, that was exactly like my data set. And they said, oh, no, we got it somewhere else. And he said, well, how come it has my initials embedded in the ocean in 18 different places? And so they finally had to start, referencing Dave Sandwell and NOAA and the U.S. Navy and the National Geodetic Agency and JETCO, which is why all those you see all those on Google Earth now, and about 10 years ago you didn't see them. But Google Earth is actually just really remarkable, because you can see here the bathymetry around Kauai and Niihau, and then the seamounts going further up. And so, I mean, the difference between what we can see now and just 10, 15 years ago is absolutely astonishing. This is the South Atlantic, and with the Mid-Atlantic Ridge running down through there. And this is the vertical gravity gradient, and the vertical gravity gradient, this is the actual satellite gravity, which is already a derivative. You can see that things like the Mid-Atlantic really sharpen up immensely, and if you have really good eyes, you can actually see some of these fracture zones running almost all the way into the margins here. So, and then you can also see here abandoned spreading centers show up just beautifully in the vertical gravity. Well, it shows up also in the satellite gravity as well. And then in our database at UT, we have all sorts of magnetic anomalies, which are pics from, you can see a ship ran across like that and ran through there. And then the fracture zones are blue, which we picked off of the satellite gravity data. And then large igneous provinces show up here in the Wallace Ridge, the Rio Grande Rise, and then Auckland Plateau. Northeast Georgia Rise, which I'll talk about a little bit tomorrow. Okay. And then this I superimposed our data set on Sandwell's gravity data, so you can kind of see where we pick things out from that. And so this is just comparing our fit from 2017 at 135 million years ago and Bullard Everett Smith, and they're actually remarkably similar. So it's amazing how well a lot of people did without satellite gravity and without knowing where the fracture zones and everything were. And then this is just showing, this is getting into the time scale thing. There's a large igneous province that came out here in Brazil, Paraná, and depending upon which time scale you have, it winds up causing different problems, and that's why we prefer the one time scale, because at least we have opening in the South Atlantic, because there were some magnetic anomalies down here on M10, Cron M10 and 130, and if you used one time scale, then this thing didn't erupt until after those anomalies were formed. So, and then you can see how it opens up, and that's all our data. And then now, moving on to Cuba, finally. This is the satellite gravity data for the Gulf of Mexico here. You can see the Yucatan Peninsula. You have really sharp eyes. You can see where the Chicxulub hits in there. Cayman Trough, and then Cuba here, Caribbean, and Nicaragua rise there. And then, of course, the subduction along the margin here. Gulf of California with offset, long offset transform faults and very short spreading centers. And then this is the satellite gravity. They now have a lot of, they now incorporate the continental gravity as well. And so then this is Cuba here, and the Bahamas platform coming out here, and then Yucatan in this area here.
Larry, you can really see Chicxulub on that one.
See what?
Yeah, it should be somewhere in there.
Right there, I can see it from here. Right.
Okay.
The bullseye of the 66 million year old meteor impact that did the dinosaurs in.
Yeah. Which I'll talk about at the very end.
Okay.
So,
See better.
yeah, there you can see it really nicely in there. Okay. These are the various plates that we have divided this whole area into, and you can see down here in northern South America, it's just really a mess, and so we've had to cut it up and slice it into everything. And then Aruba and Curacao all have to be essentially on their own little plate, which causes all sorts of problems. And, these are the magnetic anomalies. normal seafloor spreading here, the Galapagos rise coming through here, so you have another plate bound. You have a triple junction in here, and then a very few and somewhat controversial anomalies picked in the Cayman Trough, and nothing here in the Caribbean. And we now have, due to the very latest satellite gravity data, there's actually a fairly good abandoned spreading center in the Gulf of Mexico. But again, there's still magnetic anomalies there, and partly that is because, particularly in like the Gulf of California, you get very nice magnetic anomalies down here. As you go into an area where you get a lot of terrestrial sediment coming in on top of the spreading center, you don't get nice magnetic anomalies frozen into the seafloor. And so our age on the opening of the Gulf of Mexico is a bit, well, we're not quite sure, but a lot of it has to do with, well, we think it had to have started opening by this time, and we think it probably ended opening at this time based on geology around here, some of which may be correct and some may not be. But in the central Atlantic, you have beautiful magnetic anomalies. This is anomaly 34, and then this is the Cretaceous quiet zone, which went from about 83 million years to not at about 121 million years ago. And then we actually think that the central Atlantic probably started rifting at about possibly as old as 195 million years, but actually started active seafloor spreading by about 178 or so. This is one thing. This is the actual satellite magnetic data enhanced with shipboard magnetics data. And at first I thought, wow, this is really good, because it's almost like somebody used a Hubble telescope and you got these really nice delineations which looked a lot better. Turns out, you know, one of the things you can do with geophysics, the old joke is, you know, the guy gets really upset because his boss keeps wanting him to show different things, and finally he says, well, to his boss, well, what do you want me to show you, so that he can change the algorithms and stuff like that. And this is actually simply takes, you know, anomalies here, and if it's got a crossing here and crossing here, it draws the line between the two. So you have to be careful at what you see. And this is just showing how bad it can get in places like the South Atlantic. All right, these are the pieces we're talking about. And then we've got Cuba divided into a northern belt up here, which in fact is actually part of the Bahama-Florida platform here. And then the rest of this stuff all came from various different places. This piece over here was probably originated down here, and then there's some highly metamorphosed things that came through a subduction zone and then popped up through the rest of the crust.
Goodness.
And then getting back to Manuel, who we worked with, I wanted to show this in Havana, and in his paper in 1969, he's talking about orthogeosynclines and eugeosynclines and everything like that, and how anybody could understand what was going on in Cuba. Trying to do vertical tectonics is beyond me. In '65, they actually had some pretty good structural geology that had been done, and a lot of it stands the test of time. They recognize these metamorphic, these Los Pinos and the Escambre massifs here. There's another one over in here, and then possibly another one over here. And then they have the Cretaceous early tertiary fold belt in here. And then they had acidic plutons as well. And so they had a pretty good structural map, but nobody quite understood how things got there. And so this is the Bahamas Bank here, and then I'm going to show you some profiles, and I'm not sure which one was next. Okay, this one, F to E, and this is what Manuel has published. And what's interesting is that you get over it here, and this is the Bahamas platform. This is also the Cayacoco and the Remedios are all part of the Bahamas platform, and you can see it goes down into here. And then all this other stuff, all the rest of Cuba, has come in from various different places, sometimes thousands of kilometers away. And Caminwani and the Plocitos is in fact ocean floor sediments and stuff that have been scraped up as this Cretaceous arc came running into the whole thing and just bulldozing it up. And all of this stuff is probably very much like the Franciscan in California, which is stuff that's been off.
What's the red material on that slide?
The red material is the Cretaceous volcanic arc, this thing here. And there's a lot of, and then these are cenoorogenic basins up here, piggyback basins as they call them. And the Cretaceous arc, I'll show you in the animations where they were formed way out on the Pacific margin of what is now Central America, but was not then Central America. And this would be what he had as eugeosynclines, and this would be the miogeosynclines. And this is the basement of the Bahamas, the purple stuff coming down through here. And then Garcia Casco and Manuel and Jim Pendel had a paper in 2008 where they had the Bahamas platform here, and this is the Cayacoco and the Remedios were along here. This was the oceanic stuff in this Proto-Caribbean Sea. This is Yucatan, and then this is some of the metamorphic ones, the Congre, the Scambre. But they also threw in the Samana, which is over in Hispaniola in the Dominican Republic. And this would be for Aptian, so this would be about 120 million years ago. And so you can see that, and then the Caribbean arc, which you asked about, which was the red stuff, is way out here. And some of the really good, interesting geology they've done is they've been able to look at the metamorphic temperatures and show how you had oceanic subduction on the Escambre, and then it was subducted down to pressures of 20 kilobars, which is quite a ways down, and then through this period of time it was down there, and then it popped back up relatively quickly, and then was incorporated into the rest of Cuba as they collided together. This is a very recent GSA day, and essentially Cuban geology doesn't go back before the lower middle Jurassic, except for there's a Socorro complex that's Neoproterozoic, quite old, and that's only found in the very bottom of wells, and they think that was stuff that they're not quite sure where it came from. But again, here's one of Manuel's papers, 2008, and you have the Cretaceous arc, collisional front coming in like this, the Caminwani and the Plocitos getting scraped up and running into things up here. And I guess I better. So 200 million years ago, what we think was happening, this was South America, Africa reconstructed, and much like Teddy Bullard showed. And then here's, you can see Texas, New Mexico, Arizona, California pretty much didn't exist. And then you have Yucatan rotated back into the Gulf of Mexico, and part of the margin of Yucatan is actually onto the Texas margin. And what's interesting is there's a volcanic Permo-Triassic granitic arc here in Mexico, and in order to put all these pieces together, we think we've got this box pretty much nailed, but we don't quite know how to get this piece in here. And these are all the bits and pieces of northern South America. And so as you start opening the central Atlantic up here, and we start moving this stuff apart, and here's essentially the margin of Cuba is, the northern margin of Cuba would be up in here, and you're getting a little ocean forming there as you open this here, and you have translation motion here, and then motion out through here. And you finally have initiation of seafloor spreading in the Gulf of Mexico, probably at about 170. And as you can see here, as the ocean floor gets older, the colors get cooler, so that the spreading center would come down through here, and run in through here. And then this is rotating out. This arc here is, you can see this arc here has been moving along. And some people consider this, Leon Silver many years ago had the Mojave mega shear coming down through here. That, I think, is actually an older thing. This is a different timing on it. And that's the production of salt in the Gulf of Mexico. Starting, and the production of salt probably happened very rapidly, possibly as short as 25,000 years. And then opening up the Gulf of Mexico. And the only bit of Cuba is this northern bit of Cuba up here, the northern fold belt. And we think that the other bits of Cuba may be down in this area here at this point in time. And then you have various blocks coming in, and this is actually part of Cuba here, coming in as part of this arc. And then it opens in the proto-Gulf, proto-Caribbean here, and then this is, we think, the Caribbean plate coming in over here, possibly originated from what is now the Galapagos hotspot. It hits the Caribbean plate, Nicaragua rise, and the stuff comes in, hits the arc, and at this point here, you can see these metamorphic bits are here, and they've gone down, and then they pop back up. You pick up part of Cuba over here, and it goes along. And then finally, only about 48 million years ago, do you actually get Cuba in any shape that we even know about it. And so a lot of people have, Cuban geology that then starts at this point, and then you have opening the Cayman Trough as you're moving the Caribbean plate and the Antilles arc, which is subducting all this older ocean crust that you can't see here. And then the Pacific, this ocean floor here is getting subducted along this subduction zone here, and eventually comes in and hits. And this was talking about this arc here that we think it's a very long and Permo-Triassic arc, and what happens is you wind up possibly leaving a small ocean basin there, and then Yucatan moves out, picks up the Chiapas block, rotates out, and then I had to change projections. And then this would be the Cambrai, this was Pinos and Cambrai there. Picks them up and then moves them northwards, and then crashes in and folds everything up and messes everything up. And then it becomes Cuban. After about 45 million years, Cuban geology becomes pretty boring. And then this is, they just recently had a drilling leg where they drilled into the rim of the Chicxulub impact crater, and they found all sorts of interesting. This is the satellite gravity showing the outline of the rim, and they were drilling into, they wanted to go into the Cretaceous Paleocene boundary, and it's really amazing how much the depth of what this impact was, and went down to almost 30 kilometers. The reason why I'm showing this is that it turns out that on Cuba there's some Cretaceous Tertiary boundary breccias that are quite interesting. And this is, we got to see the breccia there, and it is just absolutely chaotic. And it's amazing, you know, you're wandering around Cuba and how they ever identified this as being a Chicxulub impact tsunami deposit. It was pretty amazing. And so the question was, in Belize, there's also some evidence of the impact here, but you don't see any of these tsunami deposits or anything like that. And the reason is that Cuba was essentially protecting this area from any tsunamis. The tsunamis would have come out and you know, run up along these nice margins here, but when they hit a fairly high margin, they would have been able to take it. And then this is the Cretaceous Tertiary boundary, right where that hammer is. And I'm not a geologist, so I could never recognize that as being the Cretaceous Tertiary boundary. But I did find somebody, I think it was Japanese, who did a whole bunch of paleomag, and I found a paleo where somebody drilled the paleomag for. And as I mentioned, Manuel had spent a lot of time at UT because he was a good friend of Amos Salvador, because they both worked, Amos Salvador worked on whatever Standard Oil was known as, or no, Gulf Oil was known as when they were working on Cuba. And so we actually have a lot of samples from Cuba and maps and stuff at UT. And Eric Rosenkrantz spent a lot of time putting together an absolutely wonderful atlas, which I think is still one of the best pieces of work done. And now I'm moving on. I have 7 minutes to give you a tourist thing. Pardon?
You get a little more.
All right. Well, anyway, this was from April in Havana, and it was really remarkable because I guess there was a very short window of time when you could go to Cuba as an individual rather than having to go there as a group, because you can only go there as a group now. And so Ian Norton and I flew down there, and I just was out wandering around, and there's a lot of this picture. The next picture was taken literally turning around and looking across the street, and so there's been a lot of hurricane damage, and a lot of it's never been fixed up. And then this was a magnificent old structure sitting near the beach. And this is where the Havana windsurf.com people, they have windsurfers in there. And this is the Russian embassy, probably the ugliest building ever known to mankind. And that was probably some sort of communications thing up there. And if we go down to Revolution Plaza, you see these absolutely remarkable that's Chicxulub. And then this is downtown, and you get a lot of tourists, but then you also have the home of the Rita Ernest Hemingway's bar. And this is apparently one of the most expensive hotels in Cuba now, and I think it's like $400 a night, which I know by Jackson standards cheap, but as an academic, that's a lot of money. And this was at the Congress, and this is Manuel, and then some of the other people. And what's, I guess, sad about Cuba is Manuel is probably the Cuban geologist, and he was paid $30 a month. And then the price of gasoline is $4 a gallon. So people may have a car, but they don't drive it because they can't afford the gasoline. And yet, at the last day of this meeting, you can just see in the background, there was this 10-woman band. They were very good, playing for a couple hours. They got paid $30,000 for their 2-hour performance. So there's a huge difference between what scientists get paid and others. And then this is a tobacco drying barn that was, I just took a picture outside the bus. And there's still, if you get out of Havana, there's still people that get around in horse carts. And a lot of people get around on bicycles. And this is apparently one of the most picturesque parts of Cuba, Anales. And this is all sort of wonderful karst deposit here with tourist hotels. And then this is in a tobacco drying barn. And there are some absolutely stunning beaches, but they're outside of Havana. And not many people go to them. But if you go to some of the other towns in Cuba, you'll find magnificent old hotels that date back 100 years or so. There's also, Manuel's, one of the main things now is environmental change, and you can see here there's a lot of coastal erosion in here, and some of these houses were almost getting up to the edge of the cliff, and so he's very concerned about sea level rise and storm damage and things like that. There's also a lot of pollution. This was at some sort of oil refinery thing, and you could see huge amounts of smoke. That's Manuel and his wife, and he was able to buy a house there recently. And when I asked him what he wanted me to bring, he wanted Gorilla Glue and caulking material. And I asked him what about his wife, because I had sent him home with 4 bars of dial soap because he said he wanted soap. And he said, well, his wife didn't like dial soap that much. Could I get him Dove? That's when I found out there's like 30 different varieties of Dove soap. So, anyway, and there's just wonderful street art in Havana. You see things like that. And then this is right down in Havana. This is the old fort, and I don't think I'd ever want to fall into that road there. So, anyway, thank you for your interest, and I will try to entertain questions.
Very good.
Questions for Larry?
So Larry,
Yeah.
on this map, can you show us a little bit with pointer of where the Bahama platform is? And
That's a whole nother talk,
Oh,
which I'd be happy to give you. But
well, okay, we can arrange that.
the Bahamas, the northern fold belt is just this upper little sliver in this area here. So everything else came from, and then this is a fairly recent, this is the Sierra Mestre, and that's a fairly recent part of the Cayman Ridge, and it's mostly volcanics and stuff down there. But then there's other little bits in there. But the Bahama platform, you can see it actually, it would be sort of right in this little area here. Whereas the thing that came off of Yucatan, the Cumbre, is this area over here, and then the rest of it is, well, and then that's the Scambre and these little pinos. Those are the metamorphic bits that got subducted and then popped back up. So,
And the pictures you showed of the sort of remnants of Chicxulub.
Oh.
Yeah.
the Brecha, Vanales National Park is about down in this area, and so they would have been on the Congre part, but it was already moving northwards, and then also there's, I didn't show you some other pictures, but there's also some tsunami deposits. They're just on the eastern part of Havana up here.
Also from
Yeah.
the same.
Yeah. So.
What about earthquake activity in Cuba today?
There's a lot of earthquakes down in this area here, in the thousands, but they're all mostly small. But when you get down to the Cayman Trough and then over to Puerto Rico area, you get a lot of, there's still subductions going on there, so there's a lot of earthquakes in that area. So, but the rest of Cuba, not so much. No. Yeah. But,
You showed us all those nice maps of long, long ago,
Yeah.
but do you have a sense of where all this land and stuff will move in the far future?
everything south of here is going to keep moving in various directions. And so the Antilles arc is going to keep, subducting part of the Atlantic Ocean, and as this grows here. But this would be, pretty much Yucatan and Cuba and North America is all sort of nicely glued together now. So it's not going to move in relationship to each other, but Puerto Rico and stuff is probably going to move away from Cuba in that area.
Yeah, if you saw that, his reconstruction,
Yeah,
the really big fault with all the earthquake activity is just south of this slide, and it goes right under Port-au-Prince.
yeah,
So it's,
yeah. There's a major earthquake there. So, yes.
So that bounds one of the fastest moving plates on Earth, right? The Columbus Basin area, immediately behind the Antilles Arc, isn't there it's moving something like 8 to 10 centimeters a year? There's a similar slice crossed off of southern Argentina and the tip of South America. It looks very similar in terms of its geometry. Any thoughts on the dynamics that are in place there and causing that motion?
Well, you can come to my talk tomorrow at lunch. Now, a lot of people have actually, compared the Scotia Sea with the Caribbean, and there are some, superficial similarities, but I think in general there's relatively very different things going on there. I don't know if that answered.
Larry, is there active volcanism? I'm not aware of it.
In Cuba?
Along that southern border of the southern, part of Cuba?
I don't think there's any active volcanism, but there's relatively young volcanics there. But I have to go back to Eric's atlas to figure out exactly what the ages were.
well, just a comment. I don't think people really understand how revolutionary the whole concept of plate tectonics was to the geoscience. I mean, it literally happened in 66 through 68.
Well, and what's interesting is that there were people that were adamantly opposed to plate tectonics. And I remember going once to a lecture at Harvard, and I was trying to, I was a graduate student at this time, I was going to try to formulate a question, and luckily Peter Molnar was sitting behind me, and he asked an absolutely devastating question. And this guy that he had been in Santiago in 1960, a huge major earthquake there. And he was adamantly opposed to it being subduction related. And it was almost like Peter asked him which way he fell if he knew which, what the wave motion was. But yeah, I mean, and then there were people even into the 80s and stuff that still were fighting against it. And I guess, Meyerhoff, I don't know.
Oh, the Russian? Yeah.
Well, no, Meyerhoff was in Oklahoma.
Oh, that's right.
But yeah, the Russians, Belousov, I think.
Belousov, yeah.
Yeah, but the Russians, as I showed, Karasik actually understood plate tectonics and was publishing things about plate tectonics back in the late 60s. And yet the rest of Russians, in fact, when I gave this talk in Cuba, it was really interesting because they said it was so refreshing to hear something about plate tectonics because they had spent so much time listening to Russians who didn't believe in plate tectonics. And it was like they had lost almost 20 or 30 years worth of experience, although Manuel clearly believed in plate tectonics. So.
I had a really interesting experience out of an undergraduate at UCLA, and had this professor fairly early in my undergraduate career by the name of Preston Cloud, who's just very, very famous geologist, and he absolutely did not believe plate tectonics at all.
Yeah.
Some crazy idea. Well, then I went off to graduate school in Santa Barbara, where lo and behold, Preston Cloud was. And all of a sudden, this was, about 67, 68, he didn't believe it at all.
Yeah.
In 71, it was the greatest thing since sliced bread. Explained everything. And the thing that really, you begin to see for the plate tectonics, that really understanding how all the pieces fit together. How all this salt in the Gulf of Mexico got there. And that's very important if you're in the oil and gas business, because that's literally which gives you all the structures in Mexico, by and large. So
In areas like up in Alaska where you said there's well over 200
Yeah.
plates, is there a reason why there's so many there, or the composition of them, or the forces? Are they breaking up, or are they accreting?
Well, they're mostly accreting. And so, but it's probably, you know, a lot of, we've had this thing called the Plates Project, and I think it started in '84 or something like that, so it's only been going 33 years or something like that. And we get focused on certain areas, and we were, you know, a lot, and it's supported by the oil industry, and so at one point they were very interested in Alaska, the Arctic, and stuff like that. And so we did a really detailed thing. When you really look at something like that, then you all of a sudden start having to produce all these different little pieces, because you know, they slid along the Calpag Fault or something like that. And so, you know, in order to manipulate them, as I showed you in that animation, you have to be able to have every piece have polar rotation and have it related to something else and moving with respect to something else. And I suspect, I mean, well, if you get to the cratonic continents, you know, you can pretty much assume that they're all one piece, and you don't really need to worry about all these different pieces. But if you really looked at North America in detail, and particularly, you know, just the United States, you'd probably wind up with who knows how many different little pieces. But we've never done that. So, yes?
How about the possibility that as the Juan de Fuca goes underneath the North American plate,
Yeah.
that some of those pieces got pushed up to Alaska to make some of that mess?
Oh, yeah. Yeah, I mean, there's something called the Yakutat block, which is now sort of colliding in, well, it includes the town of Yakutat, but Alaska is fascinating because you had a bunch of stuff. The Wrangell plate came one way and Yakutat is coming in a different way, because all the plate motions are changing with time as, you know, subduction zones get stopped up when a continent collides with them and stuff like that. And so the Yakutat plate probably came from somewhere quite a ways further south, and then is now moving northwards and is producing the Wrangell St. Elias and all sorts of stuff up there. We've got a whole bunch of major transform faults. And Alaska itself, Dave Scholl has this wonderful thing called extrusion tectonics, and it's like all this stuff is flowing up and then winding up out in the Bering Sea and stuff like that. So lots of interesting stuff going on. Yes?
I congratulate you on a very enjoyable talk, Larry.
Well, thank you.
I think your talk beautifully illustrates how plate tectonics is really only the first order
Yes.
picture, and the plates are much more complicated and much more inhomogeneous than was envisaged at the beginning, and their behavior is much more complicated. There's a tremendous amount of internal deformation, and now we have the tools to look in much more detail. The more we look, the more we see.
And the more plates we wind up with. In fact, we had to change, you know, when we naively started this whole thing back in the 80s, when we wrote the software for it, we had a limit of 3 digits, so we only could go up to 1,000 plates. Well, we had to dump all that. And I think G Plates now has as many plates as you want. So, and if you're interested, if you go online and just type in G Plates, it's a program that's developed by Dietmar Müller, who's at the University of Sydney in Australia. And you can sit there and play with all these things. It takes a little bit of learning, but you know, they have some nice, simple plate files and stuff like that, and you can move things around, and you can, if you don't like where something is, you can pick it up and move it somewhere else. But if you don't keep track of everything, then you wind up with a real mess. So.
I'm going to ask a couple questions and this is all over here. Why do the plates move in different directions? The rotation of the Earth, you kind of think that...
I don't know if hear that. So if you could
Why do
repeat
the
that.
plates move in different directions? With the rotation of the Earth, you kind of like things kind of like drag along the same way.
Well, I'll let Jillian answer that.
Because of the plumes, right?
I've seen some very interesting movies online recently. I'm looking at chunks of the Antarctic ice shelf carving off. And it's almost like seeing the kind of complications that you describe, where they're propagating cracks, things break off, there's a real mess in some places, and things are rotating and moving backwards. And I think we need to start thinking in terms of second order plate tectonics and third order plate tectonics. So I notice you use the term plate for anything regardless of its size. But I wonder if we need to think in terms of a hierarchy of deformation and deformational elements.
Well, yeah, I mean, in fact, you know, I was using the term plates not to get into much of nomenclature, but you know, when I said there's 277 plates in Alaska and northeastern Siberia, we actually refer to them as terrains. And so they're not, you know, they're, what do you call it, juvenile plates or something? I mean, yeah. And so, yeah, there's all sorts of different size things and stuff. And I was hoping Jillian would say something about how the plates are move, and I think a lot of them, you know, there's the whole thing about ridge push versus trench suction and stuff like that, and I think the trenches actually have a lot to do with how things move, and then eventually something like India runs into Eurasia, and that blocks up the whole trench, and in fact it's still going under it, so you get Tibet uplifted, and you get, you know, double continental thicknesses and stuff like that.
So is the Pacific plate running into the North American plate or vice versa?
It's going away from
In an absolute framework, North America is actually moving slightly to northwest, but the Pacific plate is actually getting, you know, subducted over in Japan and Kamchatka, but it's also getting subducted in the Aleutian Arc, and so it's getting pulled in all these different directions, and then you get little things like the Gorda plate, which I showed, you know, was just totally deformed because, you know, it's the material is so, the plate itself is so close to the subduction zone to where the ridge was spreading that it gets totally deformed, basically. And so that's why I think the trenches do have a major impact on plate directions. So, it's all right.
I think probably the thing that I could contribute to that discussion, which I'm most confident in, is that the plates are not driven by mantle plumes.
We disagree on that.
The other thing that kind of connect a few dots for you, the John Geisman that was here last month and gave the luncheon talk. He was talking about paleomagnetics and paleo reconstructions. And literally everything you see and where the plates are, how they move through time, all that is literally because of the resolution you can now get when you go in and orient a sample and do the paleomagnetic reconstruction of at what time, what was it, which direction was it oriented, where was north. And then you have to put it on basically spherical geometry and start moving everything around on the sphere. And that's part of why you get some very strange motions, because everybody always thinks about things in 2 dimensions, and that's not the way it's working at all.
Let me ask a question to maybe both Larry and Jillian. And that question is, what do you think about true polar wander, and what would that do to a lot of these reconstructions? True polar wander is believed to be when the North Pole rotates to the equator due to mass imbalances in the system. And I just read a book by Kirschvink and Ward, and they cite true polar wander to explain some of the major extinction events in time.
Well, I think most people would say, yes, true polar wander does occur. And if you go back in time, we get things, I think it's the Devonian and Silurian, where they have the X model and the Y model, and where you get the magnetic poles wandering around in different directions. And so what hopefully you could do is you can correct for this, the idea of true polar wander, which is why, when you just mentioned what Geisman talked about,
Right.
Paleomag samples have all sorts of different problems. You have to date the rocks carefully, you have to make the measurements carefully, and then you have to take into consideration true polar wander. So it's not quite as simple as you...
It's a bit of an art.
Yeah. Yes. So, did you want to add anything?
No, I wouldn't really add anything to that. You just have to watch how it's determined. I mean, if it's calculated based on certain assumptions that aren't certain, then obviously those results are going to be questionable. You have to kind of look in between the lines a little bit. It can be a hypothesis of convenience.
It's just, I guess it's something that throws another major complication into the whole reconstruction process based on understanding of latitude based on paleomagnetism. And maybe I'm wrong, but I don't think that 15 years ago anybody really believed that true polar wander was part of the story. Am I right or wrong on that?
Well, of course, if you're doing plate reconstructions, it's another degree of freedom that you can throw in to make your models fit better, basically. It's supposed to be a sink for unexplained data. So this is why I say you have to be a little bit careful on what basis the alleged true polar wander is calculated. Because it may just be a dump for things you can't explain. Maybe that was true polar wander.
Yeah.
So I think, as Larry pointed out, it's really the paleomag measurements which should be telling us, whether this occurs and to what degree, rather than just saying, my theory doesn't fit the data very well, so I'll just let true polar wander.
Yeah, I don't want to dive into that. There are data, and there are people that have pretty convincing data sets that they show and they cite.
Well, you have to be very careful now, John, because Larry has really well highlighted just how obvious people thought that everything could be explained by geosynclines.
I know, I grew up with eugeosynclines and miogeosynclines too, so.
Anyway, I will refrain from mentioning octopoles.
Yes. Larry, question, when you were in Cuba, is there much of any oil or gas production in Cuba?
Well, actually there is. And I thought I had some pictures of some rather dilapidated oil fields, but yes, they still are producing some oil. But I just heard on the radio today that Cuba is having they're not getting as much oil out of Venezuela as they'd hoped, and so they're now putting all sorts of this rationing. And I know when I was there in April, you'd see lines that would take like 2 hours at the gas station to fill up with gas, and so we've had a serious oil shortage for quite a while. But there are some reasonable oil and gas prospects, and that, personally, that's one of the reasons why we decided to get involved with Cuba just recently again, because we figured that, if it was going to open up to U.S. companies to explore, they would be interested in knowing something about it.
Just an interesting little Cuba fact that back in the early 50s, Standard Oil actually had the concession for the entire Cuba. And come to find out, Shell, the debate was whether or not it was related to Venezuela, and that was way before any of the plate tectonics, so it was mostly just arm waving. Well, Shell absolutely wanted into Cuba. And so after several months of negotiation, they finally signed an agreement where we, Standard Oil, gave 50% of Cuba to Shell, and Shell gave Standard Oil 50% of the North Sea. One of the better, more interesting deals ever cut. And it's an example of what it was like in the 50s. That whole contract is 7 pages long.
So, good news tonight, the chairs stay where they are. But why? Because we were told to do it that way, and we do what the library tells us to do.
Somebody's using this as it's set up tomorrow morning.
But on behalf of all of us, Larry, thank you very much for a wonderful presentation. John covered the original.
Oh, great. Thank you.
And so if you could all join me in thanking Larry, and remember tomorrow. Paul Grosser, 12:15. Chairs stay where they are. We'll be here for a few minutes if you have a couple other questions. You want to keep this in the bag? And, well, everything's